$7 an hour?
I might not ever retire if I made $1 million a year.
Are we getting here?
I was a salary negotiator, so I don't know how much it worked out. I mean, when you talk about that for what grading left, I don't know what it worked out.
I'm sending it at 9.
Okay.
She always says that.
I'm sending it at 9. Are you there? Yeah. So you were yeah. Was it 5? Thank you guys. Okay, charging my $5 and that was extra.
All right, guys, here we go. We got some notes to take. I got some stuff to hand out. We have got to get going. Okay. So we are in our notes. We are on section 5, and we're ready for number C. We may or may not do all these because we got the basic concepts down. We're all paying close attention. All right. So yesterday we talked about the difference between a recursive and an explicit formula. An explicit formula gives me whatever term I want. Boom, got it. That's an explicit formula. A recursive formula, I have to build the sequence as I go, term by term by term. Okay, so we're going to write a recursive formula for this. So basically just say to yourself, all right, what would be the next term here? 48. And how did you get that? You multiply by 2. So you take some term, times it by 2, and that will give you the next term in the list. Right? So the 5th term times 2 will give you the 6th term. Now I need to remember though that I need a starting point for all this. Because if all I know about my sequence is that I'm timesing by 2, don't I need to know what I'm starting with? Because if I started with 5 and times by 2, I would get a different set of numbers, wouldn't I? Okay. So remember, whenever you write a recursive formula, you have to have your starting point. Okay, so 0.001, 0.1, 10, and 1,000. What's happening in this sequence?
Is this a problem?
This is problem D. Yes, I'm in my notes. Is this a, what kind of sequence is this? What's going on?
10 to 2.
And multiplying by 100. So this is geometric and the ratio is 100. So when it says write an explicit formula, I'm just going to go to my canned formula, my memorized formula for a geometric sequence. This is what the formula looks like. We talked about it yesterday. In my particular problem, my first term is 0.001. My ratio is 100. So there is my explicit formula. Please, I think I mentioned this yesterday, do not get crazy and try to multiply these. You can't. That one has an exponent, this one doesn't, so that's it. The nice thing about that is, look at problem E. If we want the 10th term, we're just going to put in tens. So the 10th term, this is why explicit formulas are wonderful. They give you exactly the term you want. So won't the 10th term be 0.001 times 100 to the 9th? Oh my. So what do we, how are we gonna write this answer? What is this answer? It's 1.0 times 10 to the 15. Now, let's write a recursive formula for this same sequence. Well, you already done the work, guys. How did you say we were getting from term to term? Times 100. So if you give me some term, and I multiply it by 100, won't I get the next term? And then what do I have to always make sure I include? The starting point. So that I generate exactly the 7 numbers that I want to. All right, number 6. Let's look at what's happening in number 6. I've got some sequence. Oh, A says it's arithmetic. So I have an arithmetic sequence. I know the second term is 3. I don't know the third or the fourth, but the 5th term is 24. Right? Are you with me? That's what I know. And it's arithmetic, which means that to get from here to here, I'm adding and adding and adding. Does that make sense to you? I'm adding the same number. Well, I think you should figure this out. Logic.
7.
What?
7.
7. Why are we adding 7? Well, there's lots of ways you can think about it. But kids, don't I need to get from 3 to 24? That's 21. And I need to do it in 1, 2, 3 equal steps. So if I need to cover 21 in 3 equal steps, won't each step be 7? So my common difference is 7. Now, tell me about this term. What will that term be? -4, that's the first term, that's one of the things I needed, find a sub 1. So the first term is -4, because if I'm adding 7 to go that way, I'm going to be subtracting 7 to go this way. Now I need the 7th term. 38. Now, one thing, if it's only the 7th, could I just add 7 2 more times? That'd be really easy. Now, what if it were the 70th term? Well, then I don't think I want to be adding, so I might fall back on my formula, arithmetic formula. Remember, you can find any term you want. D is 7. You want the 7th term, you put in 7 for N also. You want the 70th term, you put in 70 here. Right? Everybody like following here? Okay. Now, what if, same situation, but now it's geometric. Okay? Which means that I am getting from 3, okay, so that's not -4. I'm getting from 3 to here by multiplying,
Multiply by 2.
multiplying by 2, because here to here is a grand total of multiplying by 8, but I have to do it in 3 equal pieces, so the cube root of 8. Now, you could do this even if it weren't a number like 8. What if this were a 12? Then my grand total multiplication is 4. But if I'm doing it in 3 equal installments, it would have to be the cube root of 4. Cube root of 4. Cube root of 4. But ours was 2. So if the ratio is 2, what's my first term now?
1/2.
What? Yeah, 3 halves. 1.5. 3, whatever, 1.5, however you want to say it. What would the 7th term be? Well, again, since it's only 7, 48, 96. But if it was the 70th, then you would want to use your geometric formula probably to find the 70th term. Okay. I thought, did we talk about Fibonacci yesterday? No? Okay, has anybody heard of Fibonacci before?
Yeah.
What is it, Sydney, do you remember?
Is it like 1, 2, 4? I don't know. It's the sequence. It's like a triangle or something. But
Well, it is. It's not 1, 2, 4, but it's
oh,
something.
you add 1 plus 2 is 3 plus 2 is 5,
Yes.
plus 3 is 8.
So the sequence actually looks like this, but you are exactly right. That's how it's generated. So what Sydney is saying is, you take these two and add it, and that's how you get the next term. And then you take these two and add them, and that's how you get the next one. So the term that would come after the 13 would be 21, and then 34, and so on. So this is called Fibonacci sequence, Leonardo Fibonacci. It actually is observed all over in nature. It's definitely recursive. Would you agree with me? If I said to you, okay, here's a term, here's a term, here's a term, here's a term, can you just jump in and tell me what that term is? No, because where does that term come from? These two added together. So this is gonna be a recursive pattern for sure. What will that pattern look like, the equation? What will the recursive equation look like?
Okay, so wouldn't it kind of be like
A sub n, that's some term,
would equal like A sub. Oh,
A sub n
I
minus
know-
1 plus a n, or a sub n minus 2.
equals a sub n. Normally we write it this way, but it doesn't matter. It's exactly the same thing. This says, give me a term and the next term. And when I add those two together, I will get the term after that. Now, what the kids said, both of them were heading this direction, it was this. Do you see how those are exactly the same thing? Normally when we do sequences, we start by letting n be 1. And this is a little problematic because if we let n be 1, then it says the first term is the 0th term plus the negative first term. So that's kind of hard to grasp even though it's the correct pattern. So that's why we normally use this one, because this says take the first term and the second term, and that will give you the third term. Now what do I have to include? I need to include that the first term is 1 and the second term is 1, because doesn't it take them both to get this thing going? You can't build Fibonacci if you only have one term. Don't you have to have two to add together? So we start with 1 and 1, and then we have 2, and we have 3, and so on. Everybody okay with that? All right, that's Fibonacci. All right, number 7. Mrs. Ford assigns 4 problems on the first day of the term, 7 problems on the second, 10 on the third. How many will she assign on the 17th day? All right, little word problem. Easy. Easy. We've got 4 and 7 and 10 and so on. So what's the first thing you observe?
plus 3.
Arithmetic. Arithmetic, right? We're adding 3. How many will I assign on the 17th day? So don't I want the 17th term? Don't I want to know what's the 17th number in this list? That's first day, second day, third day. So what's my formula say? Look at my arithmetic formula. You don't have to memorize it, but you need to know how to use it. So the 17th term says take the first term plus the common difference, which is 3, n minus 1, which would be 16. Right? Now, again, kids, you absolutely can keep adding 3 till you get out to the 17th term. But if this is the 117th term, I don't think that's the way you want to go. So get used to using your formula as a kind of a shortcut to the answer. So what is that, 52? 52? 8. Repeat the problem if we assign 3, then 6, then 12. Uh-oh, you're in trouble if I'm assigning problems according to that pattern. Now we're multiplying by 2. New formula, 17th term, it's geometric now. So the 17th term is the first term times the ratio to the 16th. Oh my God. Even I'm not this mean. 196,608. Is that okay? All right, last one in 9-4. So 9-4 homework's gonna be due on Monday. Okay? Here we go, last one. Given this recursive formula, does everybody recognize this as a recursive formula? And we know a sub 1 is 3. We need to find a sub 6. Now, at first glance, okay, if I'm finding a sub 6, then aren't I gonna let n be 5? Wouldn't that give me a sub 6? So what does this say? That's 4a sub 5 minus 10. Do you see the problem? I don't know a sub 5. Right? So I'm gonna have to start up here and work my way all the way down. So what's a sub 2? A sub 2 will be 4a sub 1 minus 10. Make sure that makes sense to you because you're gonna have to do one of these on your own at some point. Okay, so 4a sub 1 is 12. Okay, so is that 2? Okay. So now what's a sub 3? 4a sub 2s minus 10. Right? So what's that?
Negative 2?
That's 8. No, isn't that negative 2? Is that what you said, negative 2? And then 4a sub 3s minus 10 would be negative 18. I'm getting close. 4a sub 4s minus 10, well, we're getting big, negative 82, negative 82. And so the one I finally want is negative 338 if I type that in correctly.
How did we get A2?
How'd you get what?
Like, how did you find the answer?
Let n be 1, if you let n be 1, then the formula says a sub 2 is 4a sub 1 minus 10, but a sub 1 is 3. So it's 12 minus 10. This says take 4 times the previous term and subtract 10. That's what that formula says. All right, now, section 9.5 is about adding. So all of the stuff we did in 9.4 was making a sequence. So this comma, this comma, this comma, this, making a list. What we're gonna do now is add them all up. So I think of it like this. If I have a piggy bank, and on the first day I put in 2 cents, and the next day I put in 5, and the next day I put in 8, and so on. How much will I put in the bank on the 17th day? Isn't that just a sub 17? Just find the 17th number. But what if I said, how much is in my bank on the 17th day? Then I don't want to just list them up. I want to add them all up, right? So we've got formulas that do that. They're called the summation formulas or the series formulas. So you'll see up here at the top, I've prepared you for some equations. So here are the equations. want you to do is write those down. We're gonna talk about what's what.
Things I didn't know.
Okay.
I didn't know.
And I really don't have time to do this, but I've gotta tell you a story, gotta tell you one story here. And it's a true story, it's in the encyclopedia. So it's not about me, believe it or not, I'm not in the encyclopedia. No, I'm not, this isn't a story about me. But, first thing I want you to notice is, see how these two formulas have R's in them? What do you suppose that means? They're geometric. So this is going to add up, this is gonna find a geometric sum. Now, so is this one. But you'll notice that this one doesn't have an end. This is your formula for an infinite geometric sum. Now, we'll talk about that, because right now, I mean, if I'm you, I'm thinking, wait a minute, what do you mean infinite? Something goes on forever and ever, and I can add it up? Actually, you can't. We're gonna talk about that in a second. Well, if these two are infinite, then guess what? This guy is your arithmetic sum. And he's the one I want to talk about real quick. This is a true story, it's documented, you can look it up. And I'm telling you this because it's so easy when we study math to take these formulas, law, cosines, Pythagorean theorem, and we just, okay, here's the formula, use it. But remember, these formulas were all developed by someone at some point. This one was developed, this is no joke, by a kid in about the 3rd grade, I think he was 9 when he did it. And here's what happened. Oh, by the way, his name was Carl Friedrich Gauss. Ever heard that word before? Gauss? Gaussian elimination. One of the greatest algebraists of all time. And he started when he was in primary school. So, here he is, and I don't remember the exact details, so I'm kind of making this part up, but let's say it's a Friday afternoon. This teacher has a room full of like 3rd grade boys, all boys. It's Friday afternoon, everybody's getting kind of antsy, so the teacher wants to keep everybody busy and in their seats. He says, okay guys, I want you to add up all the numbers from 1 to 100. Now, if this is me in 3rd grade, and you in 3rd grade, or maybe you before we have this discussion, you're thinking, okay, I can do that. Takes me a while, but I can do it. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and a 3rd grader can do that, and it keeps them busy. Well, the teacher made the assignment, and up comes little Carl Friedrich with the answer. I mean, boom. And the teacher looks at him and says, whoa, where'd that come from? Remember, there's no watches, there's no phones, there's nothing. This kid came up with this answer. And he says, teacher, you want me to find this sum. And I know that that sum is the same if I turn it around. And if I add these two equations together, 2 of these sums, look what happens when you add these 2 equations together. They're all going to be 101s. And how many 101s are you going to have? 100. So he says the sum is 100 101s divided by 2. Because that was 2 of the sums, right? So he took 50 times 101 and got 50-50. Now, was that kid smart or what? Yeah. Now, here's the deal. Why am I telling you this story? Because this sequence is arithmetic, right? Going up by 1s. He summed an arithmetic series, and our formula is that. Because what's the n? He did 100 over 2. N was how many he was adding up. Isn't he adding up 100 numbers? So he took 100 over 2. What's a sub 1 stand for? First term. What's a sub 100 stand for? Last term. Isn't that what he did? Added the first and the last and multiplied by n over 2. Right? Formula is very simple, but when you think about it, I mean, now that we've talked about it, oh, it's simple, but this, it's amazing. It's amazing. Okay, all right. Anyway, next project. Those are our formulas. So now we're gonna see how we use them. Okay, here we go. Now, summation notation. How many of you have seen the capital sigma? Probably like on fraternity row or something, you've seen it. To the mathematician, sigma means sum. So whenever you see that symbol, you're going to be adding up something, all right? Now, problem A, what am I adding up? Okay, here's how this works. I want you to start with whatever the starting number is. So if we let k be 1, what is the first number that I'm adding? This tells me I'm adding a bunch of numbers. The first number I'm adding is -1. Now, go to 2. We start with 1. Whatever this is what we start with. Now go to 2. The second number I'm adding is 1. And then I go to 3. And I'm adding 3. And then 4, I'm adding 5, and you don't have to go all the way, because you can see what's happening, right? What's happening here? We're adding by 2, the common difference is 2, which makes this arithmetic, which means, what do I need to know? How many numbers am I adding up? Well, we're starting with 1 and ending with 10. This is the beginning, this is the ending. So every whole number between 1 and 10. So how many is that? 1 to 10.
11. 10. 9.
Okay, all right, okay. Okay. There are some people who are saying, my gosh, it's 10. Yes, it is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. I don't know where 11 came from.
I said 10, you shook your head.
And I because somebody said 9 and somebody said 11.
Okay, that said 11.
So there's 10 numbers from 1 to 10. 1 to 10. Formula says that's 10 over 2. Now, the first number I added, I found by plugging in 1, and I got -1. So that's my a sub 1, that's my first term. How am I going to get my last term? By plugging in 10. So my last term is 17. And the answer looks like it's 80. Easy. All right, let's look at the next one. Doing the same thing. All right, so what's the first number I'm adding? Put in 1, so it would be 5. Now, put in a 2, what's the next one? If I put in a 2, 11. All right, let's put in a 3. 23. Yeah, Finley says, Miss Ford, my formulas over here only work for the sequence, they only work if it's arithmetic or geometric, right? So Finley says, am I gonna have to do every one? Well, let's talk about that. Would it work? Would it work? There's gonna be 10 numbers here, right? Could I figure out all 10, take out my calculator and add them up? Yes. However, it never worked. Every time, it will always work. But I want you to think about this now for a second. Think about this. What if I forgot that -1 for a second? What if I just looked at this part of the problem? I at just those numbers for a minute. So the first number would be 6. And what would the second one be? 12. And the next one would be 24. Okay, now wait a minute. If I look at just this part of the problem, can I use a formula for these? Yes, this one right here. So I'm gonna add up all 10 of those. Go with me, just be patient. First term minus first term times my ratio, which is 2, to the nth, which is 10, over 1 minus my ratio. Does that look all right to everybody for that formula? Now, let me suggest, fix this right there, that's -1, right? These are hard enough to type in, you don't need to be messing with the subtraction in the denominator. 6 minus 6 times 2 to the 10 equals, divided by -1, did you get 6138? What?
Minus 10?
Absolutely, because what, every single one of these terms is the same as these, except they've all got a 1 subtracted from them. So can't I take, as Finley suggested, take my 6138 and subtract those 10, or that 10, those 1s, and that would be the answer. Anything that looks like this is going to be geometric. When you start doing that, then it's not going to be geometric anymore, but you can do the geometric part and then deal with that plus or minus, whatever it is. Okay, so what if this had been a +5?
Add 50.
Add 50. Yep.
Wait, why did we subtract 1 or 10 instead of 1?
And what's the difference between?
Because I'm doing 10 numbers, they're all going to be subtracted by 1. All 10 that I'm adding up.
And then that division out with +5.
All right, what's missing? The number on top is missing. What does that mean? We're not stopping. We're going forever. All right, let's look at these terms. Let's put in a 1. If we put in a 1, we have 3/2. What if we put in a 2? We have 3/4. Put in a 3, we have 3/8. Are you getting the idea here what's happening? Multiplying by 1/2, so my ratio is 1/2. Now you guys, I want you just to think about this for a second. Let's pretend there is a number on the top. Let's pretend there's 100 up there. I still would start like this, right? My formula that I erased would say S sub 100 is my first term minus my first term times my ratio to the 100th over 1 minus the ratio. Would you agree with that? That's what it would look like? Tell me about this right here. That's like 0. We talked about it yesterday. When the number you're raising to a power is less than 1, the bigger the power gets, the smaller the number gets. So if you typed in 1/2 to the 100th, 1/2 to the 100th, you're going to get something times 10 to the -31st. Is that pretty much 0? So this part of the problem is pretty much 0. So what are you left with? The first term over 1 minus the ratio, which is your infinite formula. Now, Why did that work? It's not gonna work in every problem you do. Why did it work? Because the ratio is less than 1. And again, if the ratio is less than 1, the higher your power gets, the smaller it gets. Think about it. If I were doubling 3, 6, 12, 24, am I gonna be able to add that up? No. It's just gonna keep on getting more huge, right? The only way you can use this formula is if your ratio is less than 1. Has an absolute value, less than 1. Okay, well this one did. So first term is 3/2. Ratio is 1/2. So I have 3/2 over 1/2. I think the sum is just 3. Math is so cool. All right, look at D. All right, let's make anybody's eyes twitch. Okay, what AP exam are we given now that I have all these people missing?
Seminar.
I don't even know what that is.
There's stats.
Yeah, no.
Nobody. You have to take an exam for that?
Huh?
It's like a 2-hour, like,
You just
Like
like
a
talk
presentation.
during the entire time.
Like sources.
Yeah,
You like evaluate sources.
That's what I did. It's like a
See
research.
if it's like not a real class.
Okay.
What counselor check?
Okay. All right, well, you know, I don't know what's going on here, so let's let N, oh, wait a second, we're starting with 0? Okay, so let's let N be 0. That will be our first term. What is the cosine of 0? 1. Very good. You might want to put your little handy dandy unit circle over here. And remember that cosine is x. All right, so what if I put a 1 in there? What's the cosine of pi? -1. All right, let's put a 2 in there. What's the cosine of 2 pi? All right, so what's happening? We're just going back and forth, and we're adding, so isn't every pair going to cancel? So what I really need to figure out is, do I have an even number? If I have an even number, they're going 0. And if I have an odd number, then there's gonna be that extra 1 on the end. So, I'm going all the way to 12. How many terms is that?
13. Oh my
13,
god.
that one's
Now it's
13, because we started with 0, right? So if there's 13, aren't I gonna have an extra plus 1 on the end? So the sum of this is 12, or 1, not 12. Oh, now I'm doing it. No, the sum is 1.
So the 12th,
These are n values.
okay,
So it means this is the first term I'm adding, and the second term, third term, fourth term, that would be the last term I'm adding. These groupings all cancel out, and that guy's left over. He doesn't
right,
have
but
to
why do
work.
we have 13 terms instead of 12?
Okay, get out your fingers, start with 0,
But there could be
and end at 12.
0 the term.
Well, this would be a sub naught if we were doing it, but it means find the term when n is 0.
And that counts as a,
That's a term,
okay.
that's a term.
That's our first term,
Yes,
So 0 starts at.
and then there's
All
12
right.
more.
now, yes. Now we're going to add up this one. And this one is going into perpetuity.
What? He's dead.
Get a new word!
Okay. So here we go. Let's see what's happening here. If we put in a 1, so we're starting with 1, we put in a 1. What's the sign of pi?
Oh, 0. No.
One.
I knew that.
Now put in a 2. What's the sign of 2 pi? And 3 pi? Here's pi. Here's 2 pi. Here's 3 pi. Here's 4 pi. What's the sign? The sum is just gonna be 0. Because the sign of every multiple of pi is
You have to add that
0.
Oh, wait, never mind.
The answer is
No, I read it wrong.
Why is it cosine?
This is,
I got
this
it
is,
wrong.
this is pi. Cosine is Okay. Here we go. Now you're gonna write your own sigma. I can't wait to do this because we have to figure out how many terms there are. That will be an excitement for this group. Here we go. Here's my sigma. What? Huh? Oh, so Chris has discovered, observe, that this is arithmetic and the common difference is 4. Perfect, that's beautiful. Now that actually helps us a lot because this right here is going to be the explicit term of the sequence. So that when I plug in 1, I'll get the first term. When I plug in 2, I'll get the second term, and so on. But we did this yesterday. The formula, this is arithmetic, the formula for the explicit term is this, if it's arithmetic. So the nth term, which is what's gonna go right here, the nth term is gonna go here, will be my first term plus my common difference times n minus 1. Now do your distributive and stuff, so it's 3 plus 4n minus 4, 4n minus 1. Now I want you to see this works. If I start with 1, which if I'm writing my own sigma, that's what makes sense to me, because like Marin, I'm like, wait a second, I want the first term to be n equals 1. So I'm gonna plug in 1, and I get 3. What if I plug in 2? And if I plug in 3, see, this is the formula. Now, the only thing I need to figure out is, where do I need to stop? Well, don't overcomplicate it. Yes, you're gonna stop at whatever n value you plug in and get 59? Right, isn't that how I'm gonna stop? So 4n minus 1 has to be 59. So 4n has to be 60, and it looks like I am stopping with 15. Because if I plug in 15, I'll get 59, which is my last term. Because the top number is where we stop. All right, next.
Did you do it?
Okay, here we go. What's happening here? We're multiplying by negative 1/3, which means it's geometric, which means my explicit formula is this. So here's my sigma. I'm going to start with n equals 1. And I'm going to find the explicit formula for this particular sequence. Okay? So for this particular sequence, the nth term is going to be 4 times negative 1/3 to the n minus first. Remember, we do not try to simplify that. We never can. So we're just going to leave it. So that's what goes in here. And before you ask a question, just stop and look. If you put in 1, doesn't it make your exponent 0? So isn't the first term then 4? And if you put in 2, you're gonna get 4 times negative 1/3, and so on. Now, this is where we wanna stop. We wanna stop with the exponent being 10. So on top is gonna be 11. Because if you put 11 into your formula, wouldn't that give you the last term there? That's all there is to it. It's so easy to use sigmas, write sigmas, and everything else. All right, number 3. This will be the last one we do today. A quarter section of a stadium has 8 seats along the front row. We may do one more. Each successive row has 2 more seats than the row preceding it. Okay, so let's look at what we've got. We've got some bleachers. We have 8 rows, or 8 seats in the first row, and then each successive row has 2 more than the one preceding. So how many seats are in the second row? 10, and then 12, and so on. If the top row has 24 seats, how many seats are in the entire section? So we're going all the way down to 24, and we want to add all these up. Would you agree with me? Okay, I'd rather not, it's always an option. Could I keep listing these numbers individually and add them up? Absolutely, that's always an option. It's not very handy or time smart, efficient, but you can do it. Can you think of another strategy to add these up? Now, before you say anything, what kind of sequence is it? And I'm adding. So if I'm going to use a formula, this is the formula I'm going to use because that is my arithmetic add them up formula. Now, do I already know anything? I know the first number I'm adding is 8. And I know the last number I'm adding is 24. What do I not know? How many rows there are, right? So, I could figure that out. Certainly you could count it out or whatever, but I want you to think about your other arithmetic formula. Is it true that 24 equals 8 plus 2 times n minus 1? Just look at that for a minute and see if that makes sense to you. This means the last term. I don't know what n is, but I know a sub n is the last one. So I know it's 24. I know the first one. I know my common difference. Problem is, I don't know how many rows I have. I don't know what n is. I don't know how many numbers there are in this list. Can I figure it out with that formula? Yeah. Now, I'm sure you guys are smart. I'm sure you can figure out other ways, but I'm giving you an option here. If you can't figure it out, you can always fall back on your formulas. They will always get you the answers. So 16 equals 2 n minus 1. Did you get 9 rows?
Yes.
So then I'm going to come over here and 9 over 2 goes in there. And what is that? 32, 16 times 9, is that 144?
Yeah.
I'm totally making that up. Let me see.
That's right.
Is that right? Yep. So the question was, how many seats are in the entire section? The answer is 144. All right, we're doing one more. I know. I can't help it. We're gonna do number 5. We're gonna do number 5. Yep, 5. Oh my God. it won't be 2, 3, 4 over 9. You can do it
2,
that
3,
way.
4 over 99.
I want to show you guys, I want to show you guys an option for doing these repeating decimals. And I know if you figured out, you know, you can put them over 9, you know, 1 9 is 0.1111, 2 9 is 0.22. But problems like number 6 kind of foil that, because number 6 has a non-repeating digit in the decimal. Do you see what I'm talking about? So I want to show you why this problem is in this section. Why in the world, and we're talking about sequences, why is this here? Well, would you agree? Think outside the box, quit watching the clock. Think outside the box. Is this decimal a sequence? Can you think of this decimal as a sequence? Look at it. If you lined up all these decimals and added, wouldn't you get 2, 3, 4, 2, 3, 4, 2, 3, 4? What kind of a sequence is that? It's geometric, and what am I multiplying by?
Third.
Well, 1,000th, 10 to the negative third, or 1/1000th. Moving the decimal point 3 places, 1/1000. Now, how many terms would I be adding up? If there's a bar over that, what does that mean? It's infinite. So my infinite formula says take the first term, which is 0.234, and divide it by 1 minus the ratio, which is, Peter, as you noticed, going to be 234 over 0.999, which if I get rid of the decimals is 234 over 999. Now, with problems like this, Peter, there is nothing wrong with doing what you did. But you understand why 6 is going to be a bit more problematic?
Yeah.
All right, so we'll do 6 next.